we wouldn't have many more trying to enter now. Um, so so my so what exactly are we after in this course? I mean, what do we want to finally get out of this course? Any ideas that anybody wants to say? I mean, what is your expectation? Um, I mean, I know this is a compulsory course, core course of our department. Um, so, what will you gain after taking this course? Any sort of idea that you have? I just wanted to understand your um, take. I mean, what is signal processing? I mean, this is, of course, digital signal processing. So, what is signal processing? Now, what do you understand by signal processing?
So manipulating the signals, maybe to extract something useful from them.
Manipulating the signal. So, what is a signal? That is the first thing that comes into mind. Later on, we will be manipulating them. Information, yeah, exactly. So it is what, and when you say stream, you sort of imply something. And what is that?
Varying with time.
Varying with time. But is it necessary that it has to vary with time?
Sir, it's a
Maybe it can
unit
vary with
of
positions.
information, but it can vary with like any certain quantity.
Yeah. So
Not
what the
maybe like
concept is?
time or something.
Okay. The most used, I mean, we will be dealing with time as the most relevant sort of variable in that case. And this is basically the independent variable in the whole process. It doesn't have to be time. It can be position, it can be other things that is varying independently. With that is, it is not really in the control of the processor. It is changing by itself, and our signal is the thing that is providing some information. Could be no information also, like a constant DC in the sense of information, theoretic information. It can be constant also over time or over position, like a whiteboard that you are seeing right now, or a constant DC signal over time. Those are also signals with basically zero information. Um, so it is the dependent variable, whether it is time or space or something else, as a function of this independent variables, time, space, or something else, is what we are after. And that contains information that we require. And in this signal processing, so to speak, we are going to develop and understand tools uh, that are required in order to process the relevant part of the, or extract the relevant part of the signal, relevant part of the information. Uh, in the signals and systems course, and also in most of this DSP course, we will be dealing with um, a linear processes. Okay, that is mostly we will be dealing with not processes, linear systems, or processing by linear systems. And what do we understand by a linear system? Any one person?
Any system which follows homogeneity and superposition principles?
The superposition principle itself actually contains homogeneity. So it is basically superposition principle that is followed. Does anybody here not familiar with superposition principle? Remember, this is only a small review, brief review of signals and systems. I just want to make sure that we are on the same page. Um, So I'm assuming that everybody understands superposition principle. So we will be dealing with systems that are we will be dealing with systems to process the signals with which follow superposition principle, and that is basically that if the system produces an output y1 given an input x1, and the system produces an output y2 given an input x2, whatever be the independent variable. Then a scalar multiplication and sum of the two inputs like a1x1 plus a2x2 produces a similar transformation of the output, that is a1y1 plus a2y2. That is essentially what we mean by the superposition principle. Okay. So in general, where are these applicable? I mean, we have a variety of fields in which you will be able to apply the techniques that you learn or the theory that you learn in this course. It can be in the field of image processing, in the field of speech processing, and what have you. I mean, there are many places where you can apply the concepts of digital signal processing, like radar signals, signals from images of space, or faraway radio signals, or what have you. I mean, although we will be mainly discussing linear systems, you would appreciate that it has its limitations. And of course, as you go on in these areas, you will get to know about more um, other kind of processing. Even in this course, we will know about a little bit about some nonlinear systems. And they are applicable. I mean, if you think of what we call speech recognition or speaker identification, or extracting presence of some object in an image, like many of you are already doing or will be doing projects with machine learning, that is also ultimately signal processing. And it is also mainly digital signal processing. So they are nonlinear methods, but if we think of nonlinear methods, of course, we cannot develop tools directly, I mean, from um, what should I say, from sort of first principles, in the sense that there is no sort of end to nonlinearity. So that it is a vast sort of domain, in the sense that there is no systematic variation that we can think about, other than, let's say, a polynomial function starting from linear and then second order, third order, fourth order. But those that easily becomes intractable based on how much data is required in order to develop such a system that models the processing from input to output. Um, so their things would be somewhat different, and they are mainly based on statistical approaches, which we will talk about a little bit in the later part of the course. So um, Anybody here seen an MRI or MRI image? Anybody or has worked or is working on magnetic resonance imaging? I mean, does anybody know what MRI is? Everybody must have heard of ultrasound, right? Um, Somebody please. Anybody not heard of ultrasound?
So it would be better if you could explain a bit about it.
So these are techniques of imaging the parts of the body, or using magnetic resonance, or using ultrasound, and these are used for diagnosis or of diseases, and that involves such tools like digital signal processing, where we need to identify certain abnormalities or deviation from normal images. So if you look at brain structures, let us say, and if there are features in there that are not what are normally seen, then we can further investigate into that area and so on. So these require tools from digital signal processing. Let us say radar-based detection of airplanes or missiles or something. These are also based on basically position and time signals that require processing in order to detect anomalies or things that are not normally present. So this is also another way, another kind of application where DSP is used. And there are many such examples that we can go on with. So the fundamental aspect here is that most of these, or if not almost all of these techniques, rely on discretization of the independent variable and also the amplitude variable, or rather the signal domain variable. So that is what is in the crux of the starting of discrete time signals and digital signal processing. So all real world signals are actually, I mean, mostly are actually continuous time, continuous space signals. If you look at the visual world, it is not discretized into pixels. Would you agree? I mean, but your computer screen, once it is digitized, that is, it is broken up into samples in space, or when you hear something on the uh, computer, the music or what have you, that is digitized in or discretized in time and also in the amplitude domain. So in order to process anything for the implementation part of it, most often, unless it is a totally analog circuit, most often we process using discretized versions of the signals, both the independent variable and the dependent variable, because it is not possible to actually represent any signal in a continuous manner on, let's say, a computer or a signal processor, a digital signal processor. Okay. And so what is the basis for that? I mean, how do we get to the discretized domain, and why can we do that? Let's say in time you have a signal in time.
So we sample the signal.
Yeah, so let us say we have a signal like this. Let us name it xt. So what do we do? As you said, may I know your name, please? I missed
So Shamak Chakravarti.
Shammok. Okay. So Shammok, as Shammok said, we sample the signal in time. So this is the time axis. This is xt here on this axis, that is the signal. And we sample it at a discrete equal interval, let's say delta, like this. So what do we get in return? That is the discretized version is a signal like this. Then it is 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 like this. And so on. So now that the time is discretized here, or the independent variable is discretized here, we generally represent it with n. And it could be anything. We represent it with n, and this amplitude is basically the amplitude of this signal x at this particular time point, which could be I times delta, let's say. This is I plus 1 delta, I plus 2 delta, I plus 3 delta, and so on. Is this picture clear? I mean, what we are saying? So we basically come from an infinite. So in order to represent this, even this segment here, let me use a different color. Even to represent this segment here completely, how many points do we need?
So infinite.
Infinite number of points, and we are transforming into basically 2 points. Okay. So there are again infinite number of ways in which we can connect these up, right? So from the sampled version, if we need to go back to the continuous time version, there are infinite possibilities of connecting those dots, right? And so herein comes what is important here. How can we ensure that after sampling, we retain all the information in the original signal xt? That is, if we use the discrete time signal, we should be able to reconstruct the original signal. That is what we mean by retaining all the information. There can be other meaning of it also, but for now, let us say it is being able to reconstruct the original signal.
So the sampling rate should be greater than the Nyquist sampling rate.
Nyquist sampling rate as in?
So twice the whole bandwidth of the signal. The sampling rate should be greater than twice.
So it is only possible when we have a band limited signal.
Yes, sir.
Right? So that there is a maximum frequency in our original signal xt, and then if we are sampling at more than twice the frequency, the maximum frequency, then we would be able to reconstruct the original signal. What are some of the ways of reconstructing the original signal?
So passing it through the low pass filter.
Just passing it through a low pass filter would do it? Any low
I
pass filter?
not any low pass filter. Like I mean, the magnitude would vary depending on the magnitude of low pass filter.
Of course, magnitude would vary,
Yeah.
but what kind of low pass filter would do it? And I mean,
The cutoff frequency should be equal to the maximum frequency of the signal.
cutoff frequency should be equal to the maximum frequency of the signal. Is that all? Any low pass frequency or low pass filter with cutoff frequency equal to the maximum frequency of the signal, is that sufficient?
Steep fall off.
Steep fall off. What do you mean by steep fall off?
So after that frequency, let's say B, then it should have a steep fall up so that the remaining frequencies component is not present.
It's an ideal low pass filter that we have to have here in order to be able to reconstruct the original signal. It's not just a steep fall off, it is an ideal brick wall filter. Okay. So let me go back. So have you done the mathematical transformation from this xt to our discrete time signal xn? I mean, what how do we mathematically actually represent this xn from xt, and what that actually means, and the conversion of omega here to the discrete time frequency capital omega here? Have you was that done in signals and systems?
Convolution with deltas.
Convolution with deltas, but what is the relation between these frequencies? I mean, how do we relate the continuous time frequency with discrete time? I mean, you know that discrete time frequency has a different meaning altogether, right? I mean, different meaning in the sense of different sort of properties. It is not that like it is 4 kilohertz will convert to some particular 4 kilohertz in discrete time case. Any property that you know of frequency in when we are dealing with discrete time signals?
So it must be from minus pi to pi.
Yeah, it is. It ranges over 2 pi, and why is that?
After that, it becomes integral multiples of sinusoids.
After that, it becomes integral multiples.
Like it is that integer that n is there. That's why it becomes integral multiple of 2 pi actually.
So discrete signal in frequency domain is going to be periodic in time domain. I think I said reverse.
Discrete time signal in time domain will be periodic in frequency domain. Is that what you are saying?
Ah, yes, sir. Yes, sir.
Yeah, that is one way to put it. But what I was trying to ask is, why is it that the frequencies repeat? Why is it that it is between 0 to 2 pi or minus pi to pi or any range of 2 pi?
Fixed number of Fourier exponentials.
Saurav, is it?
Shubhadeep.
Shubhadeep. Fixed number of Fourier exponentials. What is Fourier exponential now?
So e to the power iota 2 pi by n, 2 pi by capital N into n. So it will repeat after 2 pi interval.
So complex exponentials, that is this e to the power j 2 pi by capital N into n. What is the capital N here? Akshat? What is the capital N here? Any idea? Aniket? Arsh Agarwal?
Yes, sir.
So your friend here said that uh, the complex exponentials in for discrete time signals, when you convert to frequency, that the complex exponentials are represented by e to the power j 2 pi by capital N into little n. Is that right, Shubhadeep?
Yes, sir.
So what is the capital N, Arsh?
The number of samples we take in the original signal.
No, we were talking about the capital omega part of it. That is, we are talking of frequency in the, when we consider discrete signals, we are um, it is twice the frequency. Yeah, sure. When we have a band limited signal with maximum frequency, let's say omega m, little omega m, and we sample it at greater than twice omega m, we retain all the information in the original signal, in the sense that we can reconstruct xt from xn. Okay, Shubhadev. Now what we are talking about is that we have a discrete time signal xn, and when we represent it in frequency domain, the frequency domain representation is periodic in nature. When we have a discrete time signal, we convert it with DTFT, right? With this discrete time Fourier transform, and represent it in frequency domain. So in that case, that frequency that we have, that is that runs between 0 to 2 pi. Okay. And Shubhadeep, the other Shubhadeep said that it is because the complex exponential based on which we represent the DTFT, it is e to the power j 2 pi by capital N into little n.
So I think it's e to the power j omega n only. Omega small n. That's why say e to the power j omega n plus 2 pi is equal to e to the power j omega n.
E to
So
the
because
power?
the time signal is not periodic, so
time signal is not periodic.
Yes, sir.
If it is aperiodic, you
So
are
if the time signal is not periodic, then the frequency domain signal would be continuous. So that's why,
if the time signal is not periodic, the frequency
sir.
domain signal would be continuous,
continuous.
and it will have e to
So
the
a
power.
periodicity of 2 pi because the time domain signal is discrete. So the frequency domain signal would be periodic, and it would have a period like a period of 2 pi.
Period of 2 pi. So why is it a period of 2 pi is the question. So it is e to the power minus j omega n, right?
Yes, sir.
That is how we represent the discrete time Fourier transform. It is not e to the power minus j 2 pi by capital N into n. That is applicable when we are using a periodic signal with a period capital N,
Yes, sir.
right?
So the
Then
number of samples
it
in
is
one period, that is capital N.
a number of samples in one period, that is a periodicity of capital N. Then the complex exponential is e to the power j 2 pi by capital N into n. May I know your name, please? Thank you.
Sir, Aniket.
Aniket Mundal, yeah. Okay, so in the case of the discrete time aperiodic signals, we have a continuous frequency domain representation where the omega varies between 0 to 2 pi or minus pi to pi, what have you. I mean, it's periodic with period 2 pi. Now, even in that case, how can we say that it is periodic with period 2 pi?
So because e to the power j omega has a periodicity of 2 pi.
Exactly, e to the power j omega n has a periodicity of 2 pi. And that's why in the frequency domain, it will be periodic. And when it is a periodic discrete time signal, then we have the e to the power j 2 pi by capital N into n, complex exponential, as the basis function, right? And that also is periodic. And that is basically a Fourier series representation of a periodic discrete time signal. Is that okay, Aniket?
So can you repeat the last part once again?
So it is for a periodic discrete time signal, like in the continuous time. We have, for periodic signals, the representation is really Fourier series in frequency domain. We use Fourier series. We call it
Yes,
Fourier
yes,
series.
sir.
Okay.
Yes.
And for aperiodic continuous time signals, it is the Fourier transform. Similarly, in discrete time periodic signals also, we call it Fourier series representation. And the fundamental, there is a fundamental. What is the fundamental? That is 2 pi by capital N. Okay, where capital N is the period. And we have the multiples of the fundamental, that is harmonics, representing up to 2 pi, representing the frequency domain or the Fourier series representation of discrete time periodic signals. Is that okay?
Yes, sir.
Okay. So there is something here where we are referring to this complex exponential. Why is that important? I mean, why are we representing in terms of complex exponentials? I mean, these are things that have been covered in signals and systems. I'm just trying to brush things up so that you refresh your memories. Why do we represent in complex exponential, or can we have representation in some other forms?
So cos and sine.
Cos and sines and anything else? I mean, what is the fundamental
So
aspect
it's
of
just a
this
basis
representation?
function. So we have to find a
Yes.
basis function.
So we represent the signal in terms of a set of basis functions. Okay. In continuous time, it is the complex exponential, and in continuous time periodic signal case also it is the complex exponential. We can represent it in terms of the complex exponential. Only thing is that we will have impulses at the Fourier series component points. That is sort of basis function. Similarly, here in the discrete time also, we would be representing the signal in terms of a set of basis functions. And for the periodic signals, it is e to the power, in the discrete time, it is e to the power j 2 pi by capital N into n and its harmonics that create the complete set of basis functions. And e to the power j omega n again basically creates a set of basis functions where omega varies continuously between 0 to 2 pi. Is that okay? I mean, have you been taught to think of basis functions? There were many problems in Oppenheim and Wilsky, as far as I remember, with this idea. Orthogonal or orthonormal basis functions. Nandram? Harsh?
Yes, sir.
Yeah, so are you guys familiar with the orthonormal basis functions, orthogonal basis functions?
Yes, sir.
You were taught those things. Anybody
Yes.
disagree? Okay, so that's good then. That makes it easier. Um, so now the question is, when we consider, so that is the signal part of it. We will be discussing more about the signal space and basis functions that later on. And let us just continue with the idea that we started here, is the sampling part of it, where we do that. Next, okay, so whatever operation we are doing, we will be doing, we have some input to a system, xt or xn. We will be mainly, we will be dealing with discrete time signals here. We said that we will be dealing with linear systems here. We get an output yn. So in general, we will be representing with n, and you know that it is not necessarily time, can be other things, and it can be multiple independent variables at the same time, and x and y can also be vectors. Okay, so that is generalization to multiple dimensions. So here, in order to go from xn to yn, we said that we will be dealing with linear systems. And what makes it easier to deal with is to have shift invariance or time invariant system, that is an LTI. Everybody familiar with this LTI system? I mean, anybody who does not remember what an LTI is? So what is the advantage of having an LTI? I mean, that is not changing. The property of the system does not change with time. That is, it is not adaptive, which is not true of most systems. But okay, it's a start to assume time invariance and go forward. What is so nice, so to speak, about a linear time invariant system in terms of describing the system mathematically?
Sir, it can be characterized by its impulse response.
Exactly. So there is only one thing that you need to know about the system, and you know everything about the system. That is, you can predict any output given any input. I mean, given any input, you can find out what the output would be of an LTI system if you know its impulse response. That is, if you know if xn is the unit impulse, this is delta n, that is an unit impulse at n equal to 0. And for this, if you know what the output yn is, which we call hn, if we know this, then we know the entire system, in the sense that we can predict the output of any input that is given to the system. And how do we represent that? That is simply for any general input xn, to an LTI with an impulse response hn, the output yn is given by it. I mean, most of you should be, I mean, all of you should be knowing this, not most of you. Someone just say it. I mean, it's okay. I know that you know. So just say it.
xn convolved with hn.
Xn convolved with hn. And everybody familiar with this operation of convolution, right? How do we write it? We write it as x n minus k times hk, and this is sum over n equal to yk, right?
So reverse. Yn sum over k.
What was that?
Shubhodip.
Okay, Shubhodip Hajra again. So at least some people are paying attention. So it is yn.
That won't cause any problem, I guess, because you have just switched the n and k variables.
No, actually, it will cause a problem. I was expecting this from someone, Bisho Basu, right?
Yes, sir.
What it will cause a problem? What would be the problem?
So did you write there h of n?
No, I did not write the h of n.
Oh, okay. So if you wrote there h of n, then it would be fine.
Yeah, and also, yeah, there is a sign change here also. It should be k minus n. No,
Yes.
sorry, no, n minus k. Hk. Okay. Sum over k hk into x n minus k. Is that all right?
Yes, sir.
Okay. So now, what are the properties of this system that we can determine from this hn or hk? I mean, simply by looking, if you are given a plot of hk or hn, okay, simply by looking at it, what are some of the things you can say?
Causality.
Causality. So how can we tell causality? Someone else, please.
H of n is 0 for n less than 0.
H of n is 0 for n less than 0. And what is the physical significance of that? I mean, why it should be like that?
Before the impulse response comes, and there is no output.
So it should not have any output for a future input.
It should not have any output for a future input. So since hk is the output of an impulse, unit impulse at 0, n equals 0. If we have components before for negative n, that would mean that before the impulse, there has been a response due to the impulse, which would defy causality. Okay, and that is because future inputs, future inputs cannot determine the current output. Okay, so that is causality. Anything else?
Bibo stability.
Can you say that simply by looking at it?
I mean, you can check if it's absolutely summable or not. So if you've been given the function, you can.
Yeah, I'm saying just looking at the plot.
Memory.
Memory. What is that? How do we say?
So the impulse response should be a delta function.
Unless the impulse response is a scalar multiple of delta function, it is
So
the
if the
system
system has memory.
memory. Exactly. Anything else? Simply by looking at it. I'm sorry, I did not get your name. So who said about Bibo stability?
So Alicia.
Alicia. Alicia, so she made a point. That's true. We will come to that. Anything else that we can say about the system by simply looking at the what should I say? The impulse response. If you are given a plot of it, let's say any plot is feasible. Two things we have done: causality, memory. Anything else? How about the duration of the impulse response? Is it finite or is it infinite? Does that say anything about the system? So you have heard of finite impulse response systems, infinite impulse response systems, right? FIR, IIR. Anybody not heard of FIR, IIR?
So heard but not studied extensively.
Okay, that's okay. Let us say, but that's okay that you are not studied extensively, that you have not studied extensively FIR and IIR, but something um, is important here. What a finite impulse response means and what infinite impulse response means. Okay, what is the Fourier transform of the impulse response? What does it represent?
It's transfer function.
The transfer function of the system. So if Hn is finite, that is, it is of a finite duration signal, what happens to the Fourier transform of that?
So in frequency domain, it would be like infinite. The span would be infinite.
Span would be infinite. So can we say something about the system then, based on just looking at Hn?
That's not a band limited system.
Exactly. So if we have a finite impulse response, it is not a band limited system. And obviously now, if it is an infinite impulse response spanning the whole time domain, then it is a band limited impulse response system.
Sir?
Yeah.
Sir, I have another class at 11 o'clock. Can we please
Yeah,
leave?
sorry. I saw, yeah, sure. I will stop here and we will meet on Monday and continue a little bit more about this brushing up. And those who do not have class, I am here for a few more minutes only to take questions. I will not be teaching anything anymore. Okay, you are free to leave. If you want to leave and have other classes, you are free to leave. We'll